Hello, this is Concrete Path, and the lecture here is losses in pre-stress concrete. So this is actually the loss of the pre-stress. I would say loss of pre-stress. Let's remove this. I would say loss of pre-stress. So this pre-stress loss is because of when we do tensioning of those tendons. At that time there might be some loss, and during the transfer of that force, during the transfer of that uh, pre-stress force from steel to concrete, there's also possibility that there is a loss of that what you call as pre-stress force. So I would say there we have two kinds of losses. One is your time dependent, and one is your time independent, and one is your what we call as immediate. One is your immediate loss, and one is your time dependent loss. And if we talk about immediate loss accounts that we have, one is your what you call as elastic shortening. Elastic shortening is your number one. Number two is your slip, anchorage slip. Third one is there. Third one we call it as frictional loss. And on the other side, we would say time dependent losses include your creep loss, shrinkage loss, and relaxation losses. Let's take the what you call as immediate loss first. Let's go for the immediate loss first. Let's talk about the elastic shortening. Elastic shortening. Elastic shortening. Elastic shortening. And first thing is there, this elastic shortening occurs both in your pre-tension and as well as in post-tension. It happens in both the kinds of beams, pre-tension and post-tension beams. So if we talk about the first one, that's pre-tensioned pre-stress concrete beams, pre-tensioned PSC beams. Let's go for that one. So what we do here in the pre-tension beam, we have already, before the casting of concrete, we are applying the pre-stress force on the steel wire. Okay, on the steel wire we are applying that pre-stress force earlier. After that we are going to have that what you call as concrete there. Let's say this is concrete, and what is going to happen when we cut that, let's say this was anchored, and when we cut that here, when we cut the bar, it's going to apply that compressive force on this what you call as concrete. So it's going to apply that compressive force on that this concrete, and because of this compressive force on the concrete, what's going to happen? There's a chance of elastic shortening, that your concrete is going to shorten by some delta, equals to PL by AE. Delta equals to PL by AE, and we can call it as delta elastic shortening in the concrete equals to PL by AE. Can we say that this is equals to PL by AE? And same shortening would be happening, same kind of shortening would be happening for the steel also, in the steel also, because of the bond action, or we can say because of strain compatibility. So same kind of loss. So once they are having a bond and they're having strain compatibility, you apply compressive force on the bar, and that gets transferred to the concrete. So they are going to shorten, both are going to get shortened by some delta, and that delta is same. Now if I say that this is your delta in the delta elastic shortening in the concrete, and that equals to PL by A concrete, E concrete, and that's also equals to delta steel. And what is the delta steel? I would say, how is the delta steel equals to, what is the equation for delta steel? Is that stress in the steel, is that stress in the steel, stress in the steel divided by modulus of elasticity in this of the steel. Yeah, actually we can write here in this way that we know strain equals to, we know stress is equals to stress, we know stress is equals to strain into modulus of elasticity. So if I write stress in the steel, that would represent as P in the steel, that would represent as P in the steel, and that equals to strain. Let's say delta is same, because delta is same, we can write here is this one as delta ES, and that is in the steel, and you have E also divided by total length L. So if I substitute here that delta ES value here, that is PS L by E. Here we can write steel, E steel. So that is also in this way we can write sigma L by E, sigma L by E. So finally I can say this equation, this part and this part can be equated. So P by area concrete, L by EC equals to P steel, L by ES. And I can say this is your stress in the concrete section. You are having some concrete section and you are having some P force. So this is the stress in concrete, FC. So I can say this is FC by EC, and we can have this multiple also at the top, ES. That's PS. I can say PS equals to stress in steel equals to FC ES by EC. But this stress is in the steel because this is the shortening of the steel. So I can say because there is shortening of the steel. But what was the pre-stress concrete all about? You are applying the stress in the steel. So actually what you are doing actually there in the initial case, you applied some tensile force of P. You applied some tensile force of P in the steel. Because of that, I would say you elongated that steel by some, let's say 30 mm. You increased the that elongation. You increased the length of the steel wire by 30 mm. Okay. Now, because of that, the stress in the steel wire was developed equals to, let's say, some 1500 megapascal. Some stress was developed in the steel wires equals to stress 1500 megapascal, based on the concept of stress proportional to strain. Stress equals to strain delta by L into ES. So because of that, now I would say because of the shortening now the steel wire has shortened by some effect that we call as elastic shortening. So your some part of that elongation that you tried to perform initially by the jack, that has been lost by this elastic shortening of the concrete. So initially you are applying this stress on the wire by let's say you elongated the wire by 30 mm, and because of that stress in the steel wire got developed equals to 1500 megapascals. But now when we cut the wire, and that tries to come back, and it's going to shorten the concrete, and based on this compatibility of that strain, the steel wire is also going to shorten. And because of that delta loss, because of this delta loss that we have, because of the delta loss, let's say that we have lost 5 millimeters of that total 30. So that means how much stress we have lost, in the steel wires. So that equals to, I would say that is equals to 5 millimeters by total. Let's say that out of the total, let's have a general value that for 30 millimeters we have stress 1500 megapascal. 50, that means stress lost is some 200-300 megapascals, that depends on the value. So we are saying that there's loss of stress. That's what is all about, that loss of stress. That's all about what we call as loss of stress. Okay, so now I would say your equation was in this way, that because of the P force applied on the concrete, there is elastic shortening of the concrete. And that is equals to P L by area concrete E concrete, modulus of elasticity of concrete. And that is also equals to delta elastic shortening of the steel because of the strain compatibility. And that equals to, we have the equation that equals to P L by AE. This is also P L by AE, but we are writing stress L by E. where the stress is this one, this is actually the, we can write this is the loss of the stress, because this is shortening. So I can write this is the loss. So if I write now this is the loss, if I write this is the loss now, PL in the steel, this is the loss of the stress in the steel, PL. So I can write this is the loss of the stress in the steel, PL. So finally our equation becomes that your stress of loss in the steel equals to some FC times ES by EC, where your ES by EC we can write this is your modular ratio. This is your modular ratio. So finally I would say loss of stress in the steel wire, steel tendon, because of elastic shortening, that equals to F loss, because of elastic shortening that equals to M times FC, M times FC, M times FC, where your FC is the stress, where what is FC actually? I would say this is the stress, in concrete, at the level of what you call as those tendons, at the level of tendons in that section, actually, why we are saying at the level of particular tendon? Because of the strain compatibility, because of strain compatibility, we are saying this compatibility. So this is very important statement. We are saying at the level of that particular tendon in which we are saying there is some loss of stress. Let's have that picture. I would say this is your cross section, and neutral axis is here, and your steel wire is somewhere here. This is your steel wire, and at that location there is some force of P, and I would say there is some stress developed P by A. There's one more stress, PE by Z, maximum fiber PE by Z. That's top is having tensile, bottom compressive, and there might be some load also, dead loads. There might be some loads also, bending moment. Let's say there is some M also, plus minus M by Z. But we have to calculate the stresses, because our steel wire is where? Our steel wire is where? Steel wire is actually at this location. So we have to calculate the stresses at this location. Stresses at this location, at the level of stresses at the level of steel wire, So I have to calculate the stresses in concrete at the level of steel wire. So our stresses would be that we can call it as FC, that equals to P by A. Then we have this one positive P E. This is your moment. My by I, moment is equals to M, and then after that we have y by I, bending stress, my by I, where your value here is, we can write this is your value of y. This value of y is equals to E, so I can write E by I. This is your PE y by I, my by I, where your value of y is the location of that cable line, y equals to E. So this is your PE E by I. After that, third is there. I can write minus times M by Z, where your Z is actually I by Y, so we can write My by I. So but the value of Y is actually E, so we had the stresses at that level equals to this one. So this is our stresses in the concrete at that location. Then I would say the loss of stress in the steel equals to some modular ratio times FC. This is the loss of the stress because of the elastic shortening. Now this was the case corresponding to that I was having a straight tendon throughout the length. Now if I have a straight line, if I have a bent cable or a curved profile cable, let's say that I have a bent cable or a profile that's curved. Let's talk about that one. Let's say I have this one. So I have to calculate FC1 and I have to calculate FC2. That means I have to calculate stresses in concrete at ends, and I have to calculate stress in concrete at midspan. So once I got that FC1 corresponding to some eccentricity E1, and there's some load of P, there's some that prestress force of P, and so I would solve for FC1 as this way, that we have some eccentricity somewhere here, eccentricity of E1, and let's say eccentricity here is E1 and E2. We can call them as E1, E2, E1, E2. So I would say corresponding to E1, I have some stresses of P by A. I have some stress, one more stress, that is P E by I, and one more E is there, E1. Third stress is there because of the moments we can have also. We can have moments also. We can have moments also. That's at this location we have to calculate at the level of steel wires, at the level of steel wires, at the level of steel wires at this location. So that is actually ME1 by I. So this is the sum of these at the level of steel wires, that is FC1. And similarly for the FC2 we have to calculate at the location of steel tendon at the midspan. So I would say at the midspan we have some eccentricity of E2, eccentricity of E2 for the load P. So our stresses would be P by A, and one more is there, top tensile, bottom compressive. At the location of steel wires we have to calculate. At the location of steel wires we have to calculate. At the level of steel wires we have to calculate. So I would say that this stress would be equals to P E2 and divided by I, and there is one more E2. So similarly for this one, moment by Z, moment My by I, M E2 Y by I, M Y by I, where your value of Y is equals to E2 for this case. I hope you are getting this, and accordingly this is your FC2. Once you got the FC1, FC2, then we write the general equation. We'll write the general equation that we have to calculate in terms of average stress in the concrete, and the equation for that is FC1 plus FC2 minus FC1 by 2. So this is the equation for bent cable. This is the equation for bent cable when you have bent cable, and that comes out to be equals to that FC1 minus FC2. FC1, I think FC1 plus FC2. It should be plus FC2 divided by 2. FC1 plus FC2 divided by 2 when you solve it further. So this is the average stress. Then finally I would say loss of stress in the cable, loss of stress in the steel wire is equals to FC average into that modular ratio M. This is the final stress loss. And if I take the cable that's bent cable, that's parabolic cable. If I take the cable that's parabolic, there's some eccentricity E1 and E2. Let's say there's some eccentricity at the end is equals to E1, and at the midspan equals to E2. Okay. Then I had to calculate what you call as FC1, FC2. Here we had to calculate FC1. Here we had to calculate FC2. So I would say at FC1, at the ends we have some eccentricity above the neutral axis. It might be any value. It might be below the neutral axis also. So let's say I have a general perspective. Let's have a general perspective that at this location we have to calculate stresses at this location at the level of steel wires. So this is P by A. Then after that there is sagging moment. There is sagging moment because of the what you call as because of that PE. So top compressor, bottom tensile, and at this location we have to calculate this value. So this value would be equals to P E1 by I into E1. So this is PE square by I. And third stress because of the moments. Actually the moments would be 0 because it's at the ends. At the ends I would say for simply support beam moment is equals to 0. Let's have that perspective. I would say this is M by I into E1, but the moment would be 0. M would be 0 at the ends. And similarly for the midspan section, let's take the midspan section. This is your neutral axis. Your point P is somewhere here. That's at eccentricity E2. Okay, eccentricity E2. So the stresses would be P by A. So at this location we have to calculate. Let's say this is neutral axis. And we have to calculate stresses at the level of those steel wires, at the level of steel bars, at the level of tendons. Okay, because of the hogging, top tensile, bottom compressive, top tensile, bottom compressive. Third one is there because of the moments. That is sagging moment. So top compressive, bottom tensile. And at the location of steel wires we have to calculate this stress. This one is your P by A. So your FC2 we can write P by A. Then this one is positive plus this one is your actually the value of P E2 square by I, and third one is that moment. This is because of the moment, so I would write minus M E2 by I. This is your stress 2. Then once I got the value of FC1 FC2, once I got the value of FC1 FC2, then I can have that FC1, then I can write FC average for this one is equal to FC1 plus 2 by third of FC2 minus FC1. So this is our average stress. And let's say the stress at the ends, let's say the stress was somewhat, let's say this was some stress at the ends equals to FC1, and from the other side of the end also, let's say this is your beam of length L meters, and I'm saying that FC1 would be here, and at this section also there is some FC1, FC1, FC1. But at the midspan we are having some stress. It depends on the value of M now. It depends on the value of M now. Let's say the value of M was, let's say the M value was sagging. If the moment is sagging, what do you think the value here would be? Because this is negative, so net value would decrease. So net value would decrease. Can I say that? If I see that here, it depends on the value. Actually, it depends on the value. Let's say that you got some value of FC1. Where was the FC1? Yeah, this was your FC1. This was FC1. I would say this was your some value. This was also one more value, and this was 0. Actually, this was 0. So you got some value, some positive value, and here we also got some value. This is positive, this is positive, and if the moment is negative, if the moment is sagging, it would decrease the value. It would decrease the value of FC2 such that your FC2 would be lesser. So your diagram would be in this fashion, some parabolic variation. So that's why we are going that this was your, let's say this is FC2. That means we are having the equation in this way. That's some parabolic variation. Similarly, if the moment is such that it is going to increase the stress at the midspan section, I would say that let's have that again. There's one more possibility that stress variation would be in this way, that at the midspan the stress would be more, that's equals to FC2, and there is a parabolic variation after that. So then that's why we have this equation in terms of that parabolic variation. So this is your FC average equals to FC1 plus 2 by third of FC2 minus FC1. We are going to take some problems and we are going to understand what's this all about. What is this all about? So we got the general equations for all those variations. All those variations. Let's take that first one. Let's take the first problem that we have for the elastic shortening of the concrete. Elastic shortening of the concrete. That is the loss of prestress because of elastic shortening. So we have pretension beam. Pretension. This is your beam of 100 cross 300, and we have a straight wire. Wire is straight. That means we don't have to calculate FC average. We have to calculate directly FC. Straight wire is there. Straight wire. Eccentricity 50. Eccentricity equals to eccentricity of 50 millimeters. This is neutral axis. If eccentricity is 50, E is 50, and P force is 150 kilonewton. Initial force of P, Prestress force 150 kilonewton. ES by EC equals to 210 by 35 kilonewton per millimeter square. Kilonewton per millimeter square. So we can get the modular ratio. And we have to calculate percentage loss of stress in steel. Percentage loss of stress in steel because of elastic shortening of concrete. And the area of the steel wires is 188 millimeter square, and you have to calculate the stress loss in steel wire because of the shortening of concrete. Let's go for this solution. Can you tell me what is the modular ratio? Modular ratio is this equals to 6. So modular ratio equals to 6, and I would say loss of stress, F loss in steel equals to M times FC, and we have to calculate stresses in concrete at the level of steel wires. At the level of steel wires. Let's go for that. Let's go for that. So I would say you had the section. You had the section. Neutral axis is this one, and eccentricity is somewhere here. This is P force at eccentricity E. So first stress that is equals to P by A, and one more stress is this one. I have to calculate at the level of steel wires. So this value is actually some moment of PE into that value of Y. This is value of Y from the neutral axis. This value equals to E divided by I neutral axis. Okay, so I would say your stress would be equals to, stress in concrete is equals to these two values, sum of these two values. So FC equals to 150 kilonewton divided by the area of the cross section. Area cross section of the concrete 100, 300, 100, 300, 100 into 300 millimeter square. And after that we have plus 150 into 10 to the power 3 Newton. After that we have eccentricity of E. Eccentricity E, I can say 50 square millimeter square divided by I neutral axis BD cube by 12. BD cube by 12. BD cube by 12 millimeter power 4. So your stress in the concrete at the level of steel wires is equals to FC equals to 6.66 megapascal. 6.66 megapascal. That means the loss of stress in steel, that is M times FC. What's the M we have? M modular ratio 6. So I can write 6 times 6.66. That's 40 megapascal. This is the value of loss, and it's saying that get the percentage of stress loss. What is the initial stress in the steel wires? Can you tell me what is the initial stress in the steel wires? What was the initial stress in the steel wires? Can you get? So I would say initial stress in the steel wires. This is initial pre-stress in the steel wires. That is actually some force of 150 kilonewton divided by the area of the steel 188 millimeter square. This was your initial stress. Initial stress was equals to 800 megapascal. So your percentage loss of stress, percentage loss is equals to 40 megapascal divided by 800 megapascal into 100. So that's around 20%. That's around 5%. Sorry, this is 5%. 5%. So let's go for second problem. Let's go for second problem. We have a second problem that's it, which we are having some pre-stressing bed 10 meters. From one side we have fixed it. That means it is anchored from one side. Let's say it's anchored from one side. This is anchored from one side. This is anchored from one side. This is fixed, or we can say this is fixed or anchored. Now there is some steel wires. There is some steel wire also of 10 meters. Steel wire is there 10 meters. This is steel wires of 10 meters. And what we are doing, we are having some movable side. This side we can say this is movable. We can apply this pull, or we can say we can apply some pre-stress here. Let's apply some pre-stress, and there is some elongation. There is some elongation because of that. And this side, this is movable. This is movable. That means once you apply that P force, how can you apply that P force? That means you are applying some force, and because of that there is some stress developed in the steel wires. Let's say that elongation in the steel wire, let's say the elongation of that wire was, this was your delta elongation because of some force applied. This is the elongation in the wire, steel wire. This is equals to how much? 20 millimeter. This is the elongation provided in the steel wires, equals to 20 millimeters. And because of that, there would be some stress developed in the steel wires. So stress would be developed in the steel wires equals to how much stress has been developed in the steel wires. That is equals to elongation of the wire by total length of the initial length of the beam. Initial length of the steel wire was 10 meters into modulus of elasticity of the steel is 2 into 10 to the power 5 megapascals. So accordingly your stress developed in the steel wires is equals to, this should be 4, how much? This should be 0.4 gigapascal. stress developed in the steel wires is equals to 0.4 gigapascals, or we can say 4000 megapascal, 4000 megapascal, or we can say 400 megapascal maybe. Let's say this is 4 megapascal, 0.4 gigapascal. Now what we are going to do, we are having some we are going to have some beams also. Let's take 4 beams. Let's take 4 beams. We are having some 4 beams. 1, 2, 3, 4. So each beam is equals to, each beam length is 2.3 meters. So we have 4 beams that each is having 2.3 meter length. So this is your pretension. I can say this is your pretension case. Pretension case. And actually this method we call it as long line method. Long line method. Because we are making those beams, a number of beams we are making at the same time by the same wire. We are having a same wire, and that's having a length of 10 meters, and we are placing 4 concrete beams. And after that, now we are going to cut that. We are going to cut the sections here. Let's say we are going to cut the bars. We are going to cut the bars here and here and here. Now what is going to happen? Let's analyze let's analyze one of the beams. Let's analyze one of the beams. I would say there's one of the beams having the length up to 2.3 meters, and we're applying some pre-stress force of P such that the stress in the steel wires equals to some 0.4 gigapascals. This is the initial condition. This is the initial condition for one beam. Okay. And we got that how much elongation we provided to the steel wire. Because of that, we have some stress developed in the steel wires. Okay. One more thing is there, that EC for the concrete is 20 gigapascals. EC for the concrete is 20 gigapascals. And ES for the steel is also given. That means modular ratio can be solved as ES by EC, can we say that? And that is equals to 10. Your modular ratio is equals to 10. Modular ratio of 10. And one more data that's provided in the problem. Data provided in the problem that area of the steel is equals to, and this is your section of the concrete beam, that is PSC beam, that's 200, 400. Okay. Now we need to say calculate the loss of stress, calculate the stress loss, calculate the loss of stress, calculate the loss of stress in steel wire because of elastic shortening of concrete. Because of elastic shortening of concrete, can you calculate the loss of stress in the steel wires? And that is, I would say, that is equals to M times FC. That is equals to M times FC. And I would say here the eccentricity is 0. Eccentricity of the cable is 0. It's a straight line. Cable is a straight line, and it's going from the neutral axis of the section. Neutral axis of the section. So then I would say that you have this beam, you have a neutral axis, and P is applied along the neutral axis such that E equals to 0. Can you tell me what is the stress FC? What is the stress that gets developed? Is that only equals to P times A? P by A, sorry. Is that only equals to P by A? I think it's only P by A. And I have the value of P and I have the value of A. Concrete section is also I know. Value of P also I know. How do I know the value of P? Can I get the value of P from these two? What is the value of P? Initial pre-stress force is that 0.4 gigapascal into area of the steel equals to 500 millimeters square. So your pre-stress force P0 equals to 200 kilonewton. 200 kilonewton. Let's take that value here. So I would say the stress FC equals to 200 kilonewton divided by the area of the cross section. It was 0.2 into 0.4 meters square. So stress is equals to 2.5 megapascal in the concrete. So stress in the concrete, that's 2.5 megapascals at the level of steel wire. At the level of steel wire, we are calculating 2.5 megapascal. So finally, your solution would be that loss of stress in the steel wires because of the elastic shortening is equals to M times FC. Is that 25 megapascal? Is that 25 megapascals? So out of the 400, out of the this 0.4, what you have, initial stress in the steel wires was 400 megapascal, and out of that, how much you have lost because of elastic shortening? 25 megapascals. Okay, let's take that. What you have? Third problem. Third problem, for that we have 200 cross 300, and yeah, we have two different locations of those steel wires. So we have two different locations of those steel wires. Let's take a bigger picture now. Let's take a bigger picture. We have this beam. We have this beam. Let's say this is your neutral axis as per nominal concrete section, and we have the dimensions, that is 200 cross 300, 200 cross 300, and we have 15 number of 5 bars, 15 number of 5 mm diameter bars from the bottoms at 65 millimeters. At 65 millimeters, we have 15 number of bars. Let's say these are your 15 number of bars, 15 number of 5 mm bars, and at the top we have how many number of bars? We have 3 number of bars at the top, at 25 from top. This is your 25 millimeters from the top, and we have 3 number of bars of 5 mm diameter. So I would say there is some eccentricity. There is some eccentricity E1, and there is some eccentricity E2. Can I say that? So there is some P force P1, and there is some P2 force P2 at some location from the neutral axis. So I would say you have this section of the concrete. So you are applying that P1 force at this location, and you are applying that P2 force at this location at eccentricity E1 and E2 from the neutral axis. And can you calculate those stresses at those locations where your steel wires are located? Okay, so this was your problem, and after that we are saying that stresses in the wires, initial stress, or we can say initial pre-stress in the wires, is 840 megapascal. And it's also said that modal ratio can be solved as ES by EC equals to 210 kilonewton per millimeter square divided by 31.5 kilonewton per millimeter square. This is your modular ratio. Okay, we need to calculate loss of stress in steel immediately after transfer. That's right. So calculate percentage loss of stress in the steel wires. Immediately after transfer. That means after the transfer stage, you have to calculate after that, because of elastic shortening, delta ES. You have to calculate the loss of stress because of elastic shortening. So is that equals to M times FC? So we have to calculate stresses in the concrete at the location of steel wires. So we have two different problems of it. So I would say we have two different locations of the steel wires. That means we have to calculate stresses at one location and stresses at the second location. And corresponding to this, there is some stress loss of the top wires, and because of the FC2, there is some loss of stress in the bottom wires. So we have to calculate two separate values. We have to calculate two different separate values. Can you tell me the eccentricity E1, E2? Can you calculate those E1, E2? If the total is 300, and that means up to the mid there is 150, and I would say the eccentricity E1 would be then 125, and the E2 would be, let's subtract 65 minus 150, that's 85. So 85. I got those two values, 125, 85, and P1, P2 can be solved. How can you solve P1, P2? P1 can be solved as the stress in the wires is 840, and you have 3 number of bars of diameter pi by 4, 5 square. That's coming to be equals to 49.48 kilonewton. And similarly, your P2 force can be solved. That's coming out to be equals to 247.4 kilonewton for 15 number of bars. Okay, 247.4, 49.48, P1, P2. Let's go for those stresses. Can you have those stresses? Let's have the stress one. That's effect of P1 plus P2. Let's have the combined effect of P1 plus P2. So the stress would be P1 plus P2 divided by the area of the cross section. That's constant throughout those fibers. And second stress because of the P2. Because of the P2, can you tell me top compressive, top tensile? What's that? Top tensile. Because of the P2, because of hogging moment. Top tensile, bottom compressive. This is because of the, let's have the maximum value here. I would say the maximum value is P2 E2 by Z. P2 E2 by Z. This is the maximum value we can have. And third one, because of the P1, and it's above the neutral axis, so your value is, that's top compressive, bottom tensile, top compressive, bottom tensile, top compressive, bottom tensile, and the maximum value is actually some value of P1 E1 by Z. Now to calculate the stress, let's have the two different combinations here. So we have to calculate stress 1. This is actually FC1. This is stress in concrete. Stress in concrete at the level of those top, I can say top wires, at the level of top wires. So we are calculating stress in concrete at the level of top wires. Let's calculate that from this one. I would say your steel wires, top steel wires are located somewhere here. So I have to calculate stress here, stress value here, and stress value here. Can you tell me what is the values? What are the values here? We can say, what is the value we can have for this one? This value is P1 plus P2 divided by A, and this one is actually moment of P2 E2. This is the moment. And what is the eccentricity? What is the eccentricity for this location? What is the value of y equals to? Is it E1? I think it's E1. We are calculating stresses at the location of y equals to E1. That's my by I. And third one is that we had to calculate because of this moment, because of the moment of P1 E1. This is your moment, and we had to calculate at the location of y equals to E1. That's E1 divided by I, my by I. So we got the stresses at the location. And third one is that we would say this is compressive, negative, positive. Okay, let's calculate now stresses FC1. So FC1 would be equals to, then FC1 is equals to P1 plus P2 divided by area of the cross section. Then after that we have negative value P2 E2 E1 by I. And third value is that positive value. Third is the positive value P1 E1 E1 by I. So this is the first stress we have. And similarly we had to calculate stresses FC2. Let's have the FC2. So this is the stress in concrete at the level of bottom wires, So that's FC2. What can you tell me what is the value here at the level of bottom wires, at this level? So this one I can have, I would say this value is equals to, this is also P1 plus P2 divided by area of the cross section. And at this level we can say this is the value of some moment of P2 E2. But what is the value of y for this location? Value of y for this location equals to E2, eccentricity E2. So E2 by I. And third one is there, that's some moment of P1 E1, but we have the value of y equals to E2. So P1 E1 into E2 divided by I. So your stresses, we can write finally your calculation of the stress FC2 is equals to P1 plus P2 divided by the area of the cross section of the concrete. Then after that we have positive value P2 E2 into E2 divided by I. And third one is their negative value of P1 E1 E2 divided by I. So we have to just substitute the values now. We have to just substitute the values of those data. Let's go for those values. Yeah, let's go for those values. We can have those values. I'm going to I'm going directly to substitute those values. I would say your P1 plus P2, P1 plus P2 is actually, I can say, I would say one of the value is 49.48 kilonewton plus second value is 247.4 divided by the area of the cross section is 0.2 into 0.3, and this is meters, in this is kilonewtons. After that, minus P2, P2 is 247.4. Eccentricity E2 was your 85 millimeters, and its eccentricity E1 was 125 millimeters divided by the section modulus, that is BD square by 6. So I can write BD square by 6. So you can have the units accordingly. You have to check those units. And third one is there, P1. The value of P1 was 49.48 kilonewton. So better is to keep in this units. Yeah, at 49.48 into 10 to the power 3 newtons into that E1 into E1. That's 125 square millimeter square, and divided by BD square by 6. BD square by 6. BD square by 6 millimeter power 3. So that's your stress here at the level of 1. So that's stress 1. I would say FC1 is equals to FC1 is equals to FC1 is equals to you can verify that also. You can verify that, and it's coming here some value. It's some value of 5.5. You can check that. Maybe there might be error also. You can check that also. It's not a big task. Let's say the stress FC1 is 5.5 megapascals, and I would say, what is the stress in the steel wires at the location of 1? What is the stress in the steel wires at the location of 1? Is that M times FC1? So that's, what is the value of M we had? What's the value of M we had earlier? It was given to you, some data was provided to you, some data related to that M. Yeah, we can see here the value of M can be solved to, this is some value of, yeah, this is 6.67 megapascal. Yeah, this is 6.67. So actually the value here is 6.67 into some value of FC1 such that final stress loss in the wires is equals to 5.5 megapascals. That means here the value actually is, that is 0.8247. 0.8247. 0.8247. 0.8247. 0.8247. So your stress in the concrete at that level is 0.8247, and corresponding to that your loss of stress is that 5.5 megapascals. So I would say, because the strain is same at that location, strain has to be same because of the strain compatibility. Strain in concrete is equals to strain in steel at that same location of E1, and because of the modular ratio now, there's only a difference of modular ratio, as stress is proportional to strain, but your that means stress is equals to strain into modulus elasticity, and corresponding to stress of the steel, you have some E into S. You have the modulus of elasticity for the steel, and similarly for the same strain, you are having some strain, you are having some EC, and you are having some stress in the concrete. So I would say, based on this factor that this and this is same, that means your stress in the concrete, this is the loss of stress in the concrete, this is equals to what is the stress in the concrete into that modular ratio. Okay, so let's go for the second part. Let's take the second part. This is the FC2 at the level of E2. Let's solve those values. This part we already have calculated, and this part we had to substitute the values here. I would say P2 was actually, what was the value of P2? That was 247.4 in 10 to the power 3 newtons, and eccentricity E2 was below the neutral axis. This was 85. This was 85 square millimeter square divided by section modulus BD square by 6. BD square by 6. OMG. Yeah, it should not be BD square by 6. It should be BD cube by 12, because this moment of inertia. Is it? Is it moment of inertia? BD cube by 12. It should be BD cube by 12. So mm power 4. It should be BD cube by 12. This is I. This is BD cube by 12. BD cube by 12 millimeter power 4. Finally, your stress would be same. So you would follow here BD cube by 12 millimeter power 4. And third one is there. That's 47 point. Yeah, what was the force? Force was 49.48 into 10 power 3 newtons. Eccentricity E1 was your 85. And one of the eccentricity was 125, and accordingly you can check that divided by section that moment of inertia, and you would get the FC2. Stress in concrete at the level of steel 2, that is coming to be 7.7454 megapascal, and I would say stress loss at that same location would be 6.67 times 7.7454 megapascals. So that stress loss at that location of in the steel wires is equals to 51.7394 megapascals. And to calculate that percentage loss of the stress, I would say your stress in the wires is same. Stress in the wires, initial stress in the wires is same. That was given to you as 840 megapascals. Now calculate percentage loss at location 1 and percentage loss of stress in steel wires at location 2. And that would be actually FS1 by 840 into 100, and second one would be your loss of 51.7394 divided by 840 into 100. So your loss of stress in the steel wires at the location of 1 and 2 comes to be equals to 0.66%, and this one is 6.16% loss. I hope you are getting the solution. I hope you got that solution. Okay,